by Xue Xun. For the title is the Deformation and the Possible Gravitation Theory of Very Spatial Relativity. Okay, let's start.
First, I would like to thank the organizer for providing me the opportunity to present my work here. This is the outline. I will summarize various deformation versions of very special relativity and quantum geometry, and build the gravitation theory with local very special relativity symmetry. Is not torsion-free and has a natural modified gravity explanation for dark matter. This is introduction to my talk, but I will make an introduction of the motivation and background. Briefly introduction to the standard model extension, the Lorentz symmetry, and violation, and very special relativity, doubly special relativity, and deformed very special relativity. And then I will review the gauge principle approach for gravity, and our construction of with gauge principle for the gravity of the symmetry of very special relativity. And then the conclusion and outlooks. Lorentz violation is a theoretical and experimental research topics since 1990s. Kerman and Glashow, they first investigated both emergence violation in the red frame of cosmic background radiation, and these two guys built an effective field theory model for the Lorentz violation, named as standard model extension. The standard model extension is an effective field theory, mainly with consideration of general relativity coupled to the standard model. They add to the Lorentz density of the observer invariant terms that contain Lorentz violating operator combined with some coefficients. It's very effective field theory model for the Lorentz violation, and also describes general CPT violations. The full standard model extension contains operator of arbitrary mass dimension D, and the minimal standard model extension restricts attention to the operators of non-renormalizable dimension D not greater than 4. Many experiments search for the particle interaction in this background coefficient for the Lorentz violation with the background coefficient values based on this standard model extension. Here I want to stress that the Lorentz symmetry and the quantum gauge field theory has some natural contradictions. That if we describe the Gauss law for a localized charged quantum state within infrared photons involves time direction dependent gauge transformation at large distances, then the Lorentz transformation and gauge transformation are not commute. The main idea is that the creation of a charge plus Q is always accompanied by the creation of charge minus Q, and description of physics of the one charge Q without keeping track of the associated charge minus Q necessarily break Lorentz covariance. So some other people consider the simultaneously broken of the Lorentz symmetry. James Broken considered that the photon might be a ghost photon of the theory of a spontaneous broken Lorentz covariance. And Phillips says he also considered for the graviton as a ghost photon. And to break the Lorentz symmetry, one approach is that a subgroup of Lorentz group may be enough, it may be sufficient for the local symmetry of physics. This is known as the very special relativity proposed by Kohn and Glashow. And these guys, they consider the very special relativity deformation. The other possibility to break the Lorentz symmetry is considered as the quantum gravity effect, that the Planck length should not be changed under post transformations. So he introduced another invariant constant in the special relativity, in addition to the speed of light. It is known as doubly special relativity. The doubly special relativity can be realized in the non-commutative space-time or nonlinear realization of the Van group. For the general consideration that the dispersion relation or the energy momentum relation of doubly special relativity is different from very special relativity. So the main feature of doubly special relativity is the deformation deformed dispersion relation. This deformed dispersion relation can also lead to the Finsler type of space-time geometry. Let me briefly make a brief introduction to the deformed very special relativity. Kohn-Glashow proposed the very special relativity model, and then this guy deformed this symmetry as the IS-M2 model. We make a classification of the deformed Van subgroups, and then we build the space-time geometry matching to the deformed symmetry. We found that most of this space-time will be Finsler type of geometry. Kohn-Glashow argued that low energy scales maybe the local symmetry need not to be the full Lorentz symmetry. A subgroup may be enough. And if the discrete symmetry PT, CP, or CT is conserved, then the subgroup of the Lorentz group, and with this discrete symmetry, will restore the full symmetry of Lorentz symmetry. So the Lorentz value, if this, for example, if CP is violated, then the full symmetry is not Lorentz symmetry. So Lorentz violation is not connected with CP violation. They identified very special relativity subgroups up to isomorphism with T2 with generator T1 equal to Kf plus Gy, and T2 equal to Ky minus Gx, where G and K are generators of rotation and force respectively. And E2 is the generator is T1, T2, and Kz. Issue M2, the generator is T1, T2, and Kz, and S and M2, the biggest one, is T1, T2, Kz, and Kz. These guys found that due to the possible correction, quantum correction or quantum gravity effect, the SM2 group with the semi-product with space-time translation is denoted by ISM2. They admit a deformation one-parameter deformation, and this deformation have a matching matched with the Finsler type of geometry. The metric looks like this, and this symmetry, this deformed symmetry invariant equation for spin zero field in general and the long-haul equation. Other researchers, Changzhe and al., they also admit that the isometric group for special case of alpha beta type Finsler space is the same with symmetry of very special relativity. So we list here all the proper subgroups of the Lorentz group up to isomorphism. The one thing with one generator subgroup, two generator, two generator. We have two big subalgebras and four different subalgebra with three generators and one with four generators. And we seek all the natural representation of deformed generator, which inherited from the Von-Achis group 5-dimensional natural matrix representation, and we seek all the possible natural representation of deformed Von-Achis subgroup we obtained. We found that there are more than one set of solutions which could correspond to different space-time geometry. Here is a summary table. For this subgroup, the deformed one, we can classify it into several subclasses, and this number of natural representation we can. So for most cases, there are only one natural representation. In some cases we have two, and some cases we do not have natural representations. This is a summary of the invariant metric of these deformed subgroups. The common figure is like this. So it's usually have a Finsler geometrical features. So we have found that the very special relativity, the space-time is very different from the Lorentz invariant space-time. So we will try to build the gravitation theory for the very special relativity. Let's first review the general relativity in the gauge invariance approach, the equivalence principle and the local Lorentz symmetry. If for the Lorentz symmetry is locally realized, usually we know that we have a Lorentz symmetry in local physics, and combined with the equivalence principle, that means that in the space-time there always exists a free-falling observer who does not feel gravity everywhere. So we can always have Lorentz symmetry locally. That means at a point of space-time we can make such a locally Lorentz transformation. The localization of Lorentz symmetry can be realized by introducing the Lorentz connection, where the partial mu for the field can be substituted by the covariance derivative of field psi, where deep psi equal to partial psi, partial minus I over 2 A and S. SAB is the Lorentzian generator, and the A is the Lorentz gauge field, or the Lorentz connection. And we usually use the tetrad field to describe the local physics. So the tetrad field H A mu satisfied in the, we found the tetrad field to be orthonormal. So eta AB, eta is the Lorentz metric equal to d mu nu, h b mu, h b mu, or d mu nu can be expressed with the tetrad field. D mu nu equal to eta AB, h a mu, h b mu. The relation, the relation of Lorentz connection with the linear connection, that means usually the space-time index connection is this. We can derive such a relation. And usually the tetrad field basis is not a holonomic coordinate. It's not holonomic coordinate. So they will not commute. The commutation relation usually is this. So the structure coefficient F describe the is a character of the tetrad basis, and we can express the spin connection in terms of coefficient of anhonomy, the tetrad field, and the torsion. So the A can be expressed in this formula. And the curvature in terms of spin connection is similar to our well-known space-time index form. This is space-time index form. It can be derived from the spin connection expression. To describe the dynamic of gravity, the action must have the invariance group implied by the equivalence principle. So it means that it has a local Lorentz covariance. So the Lorentz gauge is a Lorentz gauge invariance, SIP. And the curvature and torsion play the role of phase strength or Lorentz connection and field-bound field. The basic field, one is connection, the other is the tetrad or field-bound field. H and A is the basic field. And this commutation gives the field strength. The T is the torsion, and R is the curvature. So curvature and torsion are the field strengths for connection and field-bound field, respectively. We have field strength, then we can build the dynamics for the gravitation. One choice is the Yang-Mills type of action, but the Yang-Mills type of action does not supply the space for gravitational coupling content, because the Yang-Mills term is the coupling content for Yang-Mills term is dimensionless. So a natural choice for the Lorentz gauge field is Einstein action. This is the Euro-Einstein-Hilbert action. Variation with respect to the Lorentz connection gives a constraint equations, which can imply Levi-Civita connection, gamma equal to this one. So it's a torsionless field. Variation with respect to tetrad gives Einstein equation. If in the presence of the matter field, the theory is not torsion-free in general. The scalar implies zero torsion, while the spinor does not. Now let's investigate the case for a local sim2 symmetry. To describe the dynamics of locally sim2 symmetry invariance theory, the gravity, one just restrict on the local transformation on sim2. So sim2 is a subgroup of Lorentz group. So we restrict the Euro Lorentz transformation with the Lorentz transformation belong to sim2. So the connection one form is like this, with the SIM2 generator expansion and 2 additional generators. To restrict on the SIM2, it is equivalent to say the constraint. The 2 terms vanish identically. So the action for the SIM2 gravity is the Euro field action, field action plus constraint conditions. We make a variation with respect to the connection with this action, get these equations. The Lagrangian multiply can be solved. So we have these 2 equations for the and for other index 3, 0 and 1, 2 we have Euro equation for Lorentz for the local Lorentz invariance. And we can decompose the spin connection in terms of contortion. Here the A theta means the torsion-free connection in general relativity. Is relation with the Trapp field, this one, and K is the contortion tensor. Is the relation with the Euro torsion is here. We recall the Lorentz case that this equation for all index equal to 0, we can prove that the connection must be a Levi-Civita connection. Now we have equation for the from this equation we have an equation for the contortion. The contortion satisfies these equations. From this equation we can see that this equation is not these 2 equations imply that the contortion must not be 0 if the Trapp field is non-trivial. So we make a variation to the Trapp field, get the Einstein equation formally. But we can see it's different from Einstein equation. We can make a decomposition of curvature also with contortion. And R theta is the curvature in general relativity with Levi-Civita connection. So the Einstein equation, this becomes a different one. For the Euro Einstein equation, we mean that the connection is a Levi-Civita connection. So here is the other part, this part, and we can express it as a energy momentum tensor. So even in the matter energy momentum tensor vanished regions, the equation for gravity looks like that there is a non-Einstein gravity part that contribute exactly as dark matter. And it should be noted that this part contribution vanish identically if the whole space is empty. That means the Minkowski space is still a solution of the equation. In the presence of matter field, if we assume that the matter field is like this, with the energy momentum tensor and angular momentum tensor, we obtain the full Einstein equation in this form, and the connection satisfies this equation. So the theory we propose here has a spin connection with torsion in general, even in the scalar field source case, and there is a energy momentum source contributed by torsion in addition to the energy momentum source contributed from matter. So we arrive at the conclusion that almost all I have summarized that almost all of deformation from Mackey subgroup, including relativity that meets Finsler type of space-time geometry. And the gauge theory approach can lead to the local SM2 gauge theory. And SM2 gauge theory is a gravity theory with torsion in general. The contribution to the curvature in general relativity sense by contortion can be regarded as a dark matter. So there are many subjects in this approach are open. One, the vacuum solution in the presence of spherical or axial symmetric source and the corresponding black hole. The second is the galaxy rotation curve. And the third is a cosmological application, the Roten-Walker-like metric, the stability check, and the relation with the Riemann-Condon theory, more cosmological astrophysics phenomenology, and Hamiltonian formulas, and the quantum case, and the gauge gravity duality. Thank you.
Any questions or comments?
How to consider Finsler geometry?
Pardon?
How to consider Finsler geometry?
Finsler geometry. No, I just mentioned here that the very special relativity symmetry is the space-time is generally anisotropic, so it's different from the whole.
So your space-time is non-commutative.
Which one is not commutative?
Your space-time.
No. It's commutative. It's Euro space-time assumption.
So you end up with the actual terms compared to the
Yeah, due to the Lorentz violation term, the natural give rise to additional term, torsion or contortion.
And they can regard that as a documented contribution.
Or equivalent description of modified gravity.
So do you have any expectation about the galaxy rotation?
I have this work is in progress, so we haven't yet.
Do you have a guess, like which direction it goes?
But I think it will modify the general relativity the result. I'm not sure it will give the correct rotation curve.
Anyone is doing or some result numerically that can be contribute 25% of the.
I don't know.
No.
It need to be a university.
Any other questions or comments? If not, let's switch in again.